Hi everybody, welcome back. This is chapter 5. I have no idea what video it is, but it's next. What we're going to do is we're going to skip over some of the theory stuff. So I'd like you to find this in your notes where we start talking about kinetic energy and temperature, the relationship between kinetic energy and temperature. So I think it's just a couple pages past where we left off with the Dalton's law of partial pressure. So skip over the kinetic molecular theory and how the kinetic molecular theory can explain the relationships we already know. I'll talk more about that tonight or tomorrow. But I wanted to get to the two other calculation equations that we need in this unit. I guess there's three. Which the first one is how we can calculate the average kinetic energy of a sample of gas. So this is not the kinetic energy of a particle, it's the average kinetic energy of all the particles in a sample of gas. And the equation that we use is 3/2 RT, where R is a different R than what we're used to. The R here is 8.3145. It's still the universal gas constant, but it's the universal gas constant in terms of joules, not liter atmospheres per kmol. It's the other R. You'll see it in your tables. And T, obviously, is your temp in Kelvin. And so what you should get from this is it really doesn't matter what the gas is. Any gas at the same condition of temperature will have the same average kinetic energy. Okay, and that's sort of the idea behind this. So gases at the same temperature, and again, it doesn't matter how much of the gas you have either. Doesn't matter what the gas is, doesn't matter what the volume of the gas is, doesn't matter what the pressure of the gas is. Gases that are at the same temperature, whether it be 5 gallons or a pint, will always have the same average kinetic energy. Kinetic energy is energy of motion, okay? So they'll do that. I know Sarah didn't like the flask pictures, but they'll do that with flask pictures, and they'll give you a bunch of different gases in flask, and they'll say, compare which flask has the greatest kinetic energy. And if they're all at the same temperature, they all have the same average kinetic energy, okay? So that's one thing I wanted to talk about. The other thing is speed. And speed is officially defined as root mean square velocity. Velocity is speed. That is a measure of how quickly the molecules are moving. We use this symbol, it's a mu, that equals root mean square speed. It's equal to the square root of 3RT over m. And again, we have to talk about these variables. R is the 8.3145 R. It's the joules. It's the energy R, okay? T is your temperature in Kelvin, and M is your molar mass. But it's not your molar mass in grams. It's your molar mass in kilograms. So we can calculate the speed or velocity of the gas particles as well. But this time it's not only temperature dependent, it is dependent upon molar mass. And what you should recognize, because this is really this, I like to use V for velocity, is that the greater the molar mass, the slower the molecules will move. Okay, so what this says, or what we will be able to calculate, is that the lightest gases have the greatest velocity. Right? Because molar mass is in the denominator, so the smaller this number is, the bigger this number will be. Whether it's in kilograms or grams doesn't really matter. I mean, you need to have it in kilograms, but a bigger molar mass will result in a smaller velocity. A smaller molar mass will result in a bigger velocity. So velocity is speed. If they ask you about speed, it depends on two things. It's dependent on temperature and molar mass. Lighter gases have the fastest speed, right? And then finally, we'll do that in class tomorrow. Finally, there's a few terms, and these are the ones that came up in the practice test. There's a few terms that we have to define that we have not yet defined in this unit. The one is diffusion, and the other is effusion. Diffusion is the spreading out of a gas and the mixing with other gases. Effusion is the funniest definition in chemistry. If you look at it, it is the passage of a gas through a tiny orifice into an evacuated chamber. So it is the movement of gas through a hole into an evacuated chamber. When we say evacuated, we mean nothing. This is a vacuum, right? There's no air there, there's no anything, okay? Lightest gases diffuse the fastest and effuse the fastest. So the lighter the gas, the faster it will effuse through the orifice, okay? I don't know, because when else do you have an orifice as a definition in chemistry? It's kind of, it reminds me of farting.
Yeah.
That's why it's funny.
Go to a small hole and then evacuate the room because it's small.
Right, but really into an it's already pre-evacuated is the thing. Lighter gases effuse and diffuse the fastest. We can get the rates of effusion and diffusion, or the relative rates, by this idea of Graham's law, which is basically what I just said here, where it looks kind of confusing, so let me just lay it out for you. If you have two gases, I always put the lighter gas on top. So rate of lighter gas, because they move faster. What is wrong? It's Monday, you can tell. I can't spell anything today. Over the rate of the heavier gas. Is equal to the square root of the molar mass of the heavier gas divided by the molar mass of the lighter gas. Now, all that this says is that lighter gases effuse the fastest. That's all that it says, but we can actually get the relative rates of effusion by using this equation. For example, let's say we have hydrogen and helium, okay? Just real quick. All right, so the rate of hydrogen compared to the rate of helium is equal to the square root of helium, which is 4, over the square root of hydrogen, molar mass of hydrogen, which is 2, right? Square root molar mass of, so it's opposite, helium over hydrogen. So the rate is equal to the square root of 2, and what's the square root of 2? 1 point, nobody knows? Nobody here knows. How come that's not a number you guys are meant to?
Simplify that.
Square root of 2 is 1.4. So what that number means is that hydrogen effuses at 1.4 times the speed of helium. It moves 1.4 times faster through that tiny orifice. On that note, we'll do more practice with this in class tomorrow. You do not need to finish the practice problems in the practice test. Just do those 3 homework questions that I asked you to do for tomorrow, in addition, of course, to watching the video. And we'll do more with effusion and diffusion tomorrow. Have a good night, everybody. Bye-bye.